This video go over how you deal with writing a proof if your original statement you're asked to prove is a biconditional or if and only if statement. What we'll also do with the examples for the proofs of the if and only if statements is we'll keep using some of the other techniques with proofreading along the way. So first of all, what happens if you're looking at the direct method for an if and only if statement? First of all, what is it that you are given? You're going to be given a statement, and it'll look like in symbols P and then the double implication Q. Now, you're going to be given these guys in terms of what looks like a sentence. So the buzzword to look for is that if and only if. Now, what do you need to worry about identifying? You need to worry about identifying those key foundational statements of the P statement and the Q statement. Please note they're not really an if and a then statement this time because remember, a biconditional or if and only if statement means you have both P implies Q, but you also have Q implies P. So both the P as well as the Q simple statements here are both the if parts and the then parts, depending on which way you're traveling that double arrow. Okay. So here's what you do. In terms of the method, this is going to be really straightforward. Step 1, determine one of the two directions to prove. So I went ahead and just picked prove if P then Q. Use the direct method. Use a different method, but somehow prove that first part. Step 2, do it the other way around. In this case, start off with Q and prove that you can get to P. Again, you can use the direct method, you can use any of the other methods that we actually haven't talked about yet, and then that'll get you the other piece of this if and only if statement. Notice the if and only if or biconditional statements are really two statements mushed together in one, so you really have twice the work involved here. Okay. Now, notice what this means logically. Logically speaking, this means that your statement P occurs exactly the same time the statement Q occurs. Okay. So let's actually look at an example. So the example I've got prepped up for us is a really awesomely classic example. It says, suppose you've got this guy n. So prove that n is odd if and only if n squared is also odd. Now, fun fact, hopefully you guys have dealt with square numbers before, and one of the things that you would hopefully have noticed is that if you're looking at your perfect squares, so I'm looking in here at n squared, so that would represent perfect squares, so like 1 and 4 and 9 and 16 and 36 and 25, and I got them all mixed up there at the end. One of the things you'll notice is that if you start with an odd number and you square it, you get a perfect square that's also odd, and the reverse also happens. So this, just from empirical data, in other words, from you just playing around with numbers in your previous part of your life before right now, you probably are believing this statement. So now let's jump from that empirical evidence of you just working around and playing with a bunch of examples with numbers into the actual proof. So the first thing is we're going to notice that this is an if and only if statement. So that does mean that we're going to have two directions. That also means that on either side of that if and only if phrase, you can arbitrarily choose who's going to be your P statement and who's going to be your Q statement. So in our scratch work over here to the side, I went ahead and chose that n is odd is our P statement and n squared being odd is our Q statement. And in terms of what we're going to be looking for, this overarching example up here at the top would be in symbols, P if and only if Q, or that double implication arrow. Okay. Now you can only deal with the implication in one direction at a time, so we have to choose whether we're going to start at P and go to Q or the other way around. We're going to start at P and go to Q just because logically when you read this sentence you're starting here on the left at n is odd and end up at n squared is also odd, so I just went in terms of normal reading. Okay. And we'll go ahead and use the direct method here. Now, one of the things that people will often do when they're dealing with the proof of an if and only if statement, because there are two directions, they will often put these little symbols that indicate which direction they're going. So in the sentence, this symbol here says you're going to start with the n is odd and end up with the n squared is odd. And that just allows yourself to remember what you're working on. It also allows your reader to know what you're working on. That is not technically part of any proof, and in fact is just some scratch work to the side. But if you see that in the future or you want to do it, that is totally something that can happen. So the first thing that we want to do is we'll get our hypothesis and our symbols up in play. We want to make sure that we say, hey, we're going to let n be our integer, and you could write it out in words, or I went ahead and put in symbols here. There's no need for us to have n is also non-negative, but I just threw it in there because I was thinking about it when I typed this up. So we know n is an integer. Let's go ahead and suppose that n is odd. And we could have actually started with this second one, but I wanted to be very clear that in the definition of an odd numbers always have to be, first and foremost, integers. Okay. So if we use our definition of odd, this tells us that n is 2 times some other integer plus 1. I use k for the some other integer. You can use any letter you want, but cannot use n because n is already in play. Okay. Now, once we know how the definition of odd plays in so far, next we're going to start looking ahead to, well, what's going on with n squared? Can we actually get to n squared being odd yet? And the answer is not yet, but we can start rewriting n squared to make it easier. So we say, all right, well, let's look at n squared. We know that n can be rewritten as 2k plus 1 just by the definition of odd. So if we go ahead and plug it in, we get that we're going to have n squared is really the same as writing 2k plus 1 whole quantity squared. Now, remember what you need for odd. We need to be able to write n squared has to be 2 times something plus 1. That something has to be an integer. Okay? So we need to rewrite n squared as 2 times something plus 1, and we'll figure out what that something is here in just a second. So in order to even contemplate doing that, with what we currently have written down, we need to expand that 2k plus 1 quantity squared. So when we multiply it out, we FOIL it out, we multiply all those middle parts together and add everything appropriately, you'll get 4k squared, that's the first term here, squared, the 2k squared. We'll get 1 at the end, that's 1 squared. In the middle here is the 2k times 1, both the inner and the outer for FOIL. So that's the 2k plus 2k to give you the 4k in the middle. Now, we're a little bit closer to getting to what we want. Remember what we want is there on the side there in scratch work. I'll put lines here to indicate what's scratch work. Everything between the lines is the actual proof. Everything outside of those two lines are our scratch work or comments. Okay? So, we now are at 4k squared plus 4k plus 1. Can we actually get this to be 2 times something plus 1? Well, let's check. We've got the plus 1, so that's no worries. So then we look at the first two terms and we say, hey, can we factor out a 2? We could factor out a 4k if we wanted to. We're not going to. We're only going to factor out the 2. Okay? So we want to factor it to grab it into the format of an odd integer. Now, in order to be an odd integer, remember, from right back up here, you had to have whatever was multiplied by 2 to be an integer itself. So we have our stuff that's potentially an integer is 2k squared plus 2k. Now, k originally is an integer. 2 is definitely an integer. So when we look at this, we say, all right, well, integer times integer, still an integer. Integer squared, still an integer. Times another integer, still an integer. 2 integers added together, still an integer. So yep, that stuff inside the parentheses is still an integer, and that is simply because we used integer arithmetic and we started with integers. Which means we can now apply that definition of an odd integer to the expression we currently have for n squared, and that gives us the conclusion that using the definition of an odd number or an odd integer, we totally have that n squared is odd. And this conclusion right here gives us half of what we need. Okay? So this is the forward direction, if you will. If n is odd, then n squared will also be odd. Okay? And that's it. Well, the first half. So let us now jump to the second half. So same statement up at the top. So we still have n is odd if and only if n squared is odd. The only difference now is we're going to go and start where we ended before. We're going to start at n squared is odd, and we're going to try to get backwards to n is odd. And I'm going to do a little bit of scratch work first. So starting point, our new starting point is at, I didn't mean to say at, oh well, n squared is odd. So if we use our definition, that means we can say n squared is 2 times some integer plus 1. And then we can say, all right, well, let's try to rewrite n in terms of n squared. Well, we know n is n squared, but take the square root, the positive square root. So then we get the square root of 2k plus 1. And what do we need this thing to get to? We need n to be odd. So we need this thing to end up as 2 times something plus 1. And then, of course, the question is what goes inside those parentheses. This strategy that I just outlined is exactly identical to what we just did when we started at n is odd and tried to get to n squared is odd. Notice the problem. There's no problem in anything we wrote until we get to the very last equals. And at that very last equals, if you're trying to actually rewrite your square root as 2 times something plus 1, what you're going to find is that's pretty much impossible to do. Okay? Not without using power series, which is not something we're allowed to use here because we're using the definition of an odd number. And if you don't know what a power series is, don't worry about it. It doesn't work here anyway. Okay? So what are we going to have to do? Well, we're going to have to rethink how we approach this problem. And this guy is going to be our first example of a proof by contrapositive. Proof by contrapositive, and let me go ahead and throw that up here. A proof by contrapositive, you're going to do this contrapositive if you get stuck. So we had just gotten stuck where we couldn't go any further because of that dumb square root. Okay, square roots aren't really dumb, but it was making our life miserable. So this is when you say, well, wait a second, maybe if I think about this in a different way, it'll help. So this is where you pull out your contrapositive, and reminder, contrapositive says you negate your P and your Q, and you flip the direction of the implication arrow. So instead of looking at if Q then P, we're now going to look at the contrapositive statement, which is if not P, then not Q. So remind ourselves. Not P, since P means n is an odd number, not P would mean n is an even number. And not Q would mean that n squared is an even number. Okay? So notice what this throws us into. Instead of looking at a problem with odd numbers, we're going to be looking at a problem with even numbers. Okay? So let's look at the proof now. So in terms of the beginning parts are going to be exactly the same. We still have n is some integer. Again, you do not need the n is bigger than 0. When I was typing, I was thinking positive numbers, well, non-zero numbers. In this case here, we're then going to throw up the negation or not p. So we're going to go ahead and suppose that n is even. We're next going to use the definition of even. Remember, even means you can rewrite the number as 2 times something. So here I rewrote n as 2 times k, where remember k is some other integer. We don't care which one it is. If you have an actual number for n, you'd be able to find the actual number for k. But as an arbitrary even number, the k would be the appropriate corresponding integer. Next, once we get this formula for n, we can then start looking at where we're trying to get to, which is we're trying to get to n squared is even. So now we'll be able to look at n squared. And at this point, we're going to be able to replicate almost exactly what we did in the other direction just a little bit ago, except now dealing with evens. So n squared can now be rewritten as 2k whole quantity squared. We'll go ahead and expand that out and get 4k squared. And remember, we're trying to get that n squared is even, so that means we need to rewrite this as 2 times something. In this case, we'll be able to factor out the 2. And the only question left in our heads should be, is that stuff inside the parentheses an integer? Well, remember, k started off being an integer. So that means this 2k squared is simply going to be an integer times an integer times an integer, which is still an integer. Okay? Then we apply the definition of even to say, hey, we've got all the pieces and parts that we need to have for the definition of an even number, which means that n squared must be even. Now, here's the extra part you put in for the contrapositive. Thus, or hence, or therefore, n squared, if n squared is odd, then n is odd by way of a proof by contrapositive. So you always have that last sentence that goes back and rewrites your if-then statement in the original not contrapositive version, and you say, hey, we prove this by way of using our contrapositive statement, and I kind of bungled the wording there at the end. Okay, so you restate your original statement right here, and then you say you use your proof by contrapositive right down there at the end. Okay. Now, that's how you can do a proof by contrapositive and broaden it out in those two parts. That would be how you deal with a proof that is from a biconditional statement or an if and only if statement. Now, let us do one more example that is much shorter for if you have an if and only if statement. So this one harks back to sets. It says, suppose you've got two non-empty sets, A and B. Maybe they're equal to each other, maybe they're not. And we're told that here is the if and only if statement part. A equals B if and only if A is a subset of B and B is a subset of A. So let's see what we would do here. In terms of symbols, if we grab out our P statement and our Q statement, our P statement here would be on one side of the if and only if. I picked on A equals B. Our Q then would be everything else on the other side of the if and only if, so A is a subset of B and B is a subset of A. Okay? And overarchingly here, we are looking at an if and only if statement, so we are looking at a statement in symbols P if and only if Q. So let's set ourselves up. At the beginning, what do we know? We know that A and B are non-empty sets. Okay, we don't know anything else about them, just pulled that first bit. Now that's true in either direction, whether we look at if P then Q or if Q then P. Now in the second line, we're going to get specific to which direction we're going. So I went ahead and did this little shorthand notation here, and this tells us we're going to start with P and we're going to arrive at 2. So we say, let's suppose that sets A and B are actually equal. Well then, what do we know about if sets are equal? Automatically, just using the definition of subsets, as long as you're not dealing with proper subsets, just using the definition of subsets, A has to be a subset of B, and B has to be a subset of A, and bam, we're done. So that takes care of one direction. This is classic. Sometimes one direction is super duper easy, and the other direction is slightly less easy. Okay. Then if we go in the other direction, so in this other direction we start off and you know A is a subset of B and B is a subset of A, we want to get back to showing that A and B, they have to be equal to each other. There's no other way to do it. Okay. So this second direction that we're dealing with, there's two main focuses. One is, it's just another example dealing with a biconditional statement, but the other is showing you how to proof write without using Venn diagrams and sets. Proof of dealing with a property of sets without using Venn diagrams, excuse me. So for this one here, here's what we do. You actually grub around in the elements. So the first thing we're going to do is we're going to pick some element of A. It doesn't matter which one. If you prefer, think of this as pick every element of A one after the other. Okay? So you pick some element of A, it doesn't matter which one. This is called an arbitrary element if it doesn't matter which one. And since we already know that A is a subset of B, this means in any element that you picked that was inside of A also has to be inside of B, and that's just the definition of using a subset. And it turns out you can do the exact same thing if you'd started with set B. So here, pick any little element of set B you want. This has to work for all elements of B. That way you can arbitrarily pick any element in B. Since B is a subset of A, you're going to get automatically that B is inside of A. And again, that's just the definition of A being a subset of B. And it looks like here on the side I have a typo. That's embarrassing. Let's fix that. All right. So, of course, then the question is, well, what next? Think back to the definition of two sets being equal. Two sets being equal mean they share the exact same set. The exact same elements. So these two lines, this first line said you picked every single element in A, and every single one of those elements in A was also in B. Now at the end of the first line, there could be elements in B that are not in A. Okay? The second line, though, says you picked all the elements in B, the ones you already knew were in A, plus any of the ones that we suspected weren't. And these guys happen to be in A, so what this tells you is you are sharing all of those same elements. And this then gets us to our conclusion. And notice, since we've gone and gotten to the conclusion that we wanted to in both the two directions, we've proved the biconditional statement as well.